So the first speaker we have is Professor Susana Gomes, Associate Professor, so from Warwick University. So yeah, welcome.
Okay, thank you. I hope the microphone's working. It wasn't, but I think I switched it on. If you stop hearing me, just let me know. The good news is, for those of you who were here last week, you can sleep for a little bit. But then wake up for Draga, because Draga's talk is going to be cool. So yeah, I'm going to go over some of the things I talked about last week, in particular on the control for falling liquid films. So I'm interested in falling liquid films. Again, as everyone said today, I don't really have to convince you that this is a nice and relevant problem, but just for completion, like you can see falling liquid films on rainy days or in monuments, and we all like to put our favorite monuments or cool things in parks that we see with falling liquid films, as you realized last week, I hope. But yeah, so this is a problem that has a lot of interest because it has applications for things like coating or cooling by heat transfer, where you want wavy surfaces. So if you think of this as an experiment, again, this is the typical experimental setup for these problems. You'll have in this experiment, people were having a flow going down a plane that was vertical. I will consider it at an angle, but I'll put that later. So usually, for certain values of parameters, these films are flat, as you can see here. But then as things get more and more complicated, you will have some type of wave or solitary wave like Fabian showed earlier that's traveling downstream. So this is like a plot and then a cartoon of what it looks like. Or when things get a bit worse, you start having 3D waves or typical chaotic behaviors. So what I want to do is, can I stop these complicated waves from developing and instead make the flow go towards something that's either flat or a shape that I care about and that I want, and then I can have it travel downstream at a prescribed speed with a prescribed shape. So the idea of how we want to do this is, okay, we have that experiment. We're going to consider like a slice in this direction. So everything I'm going to show you is a 1D PD for a 2D problem. That's, again, there's a cross-section there. So you consider a physical system that's your fluid on a plane. The full model, I'll talk about it in a moment, but you have the full model, which is Navier-Stokes equations. We will consider the closest thing to an experiment that we can do is a DNS simulation of that experiment. And what I want to do is consider reduced order or reduced dimensional models, so simpler models for the interface only or the interface in flux. Develop controls there that make the fluid do what we want it to do, and then test the controls at the DNS level to see if we can hope that this will work in a real system. So how will we do this? So last week I went through the hierarchy of models and what I meant by hierarchy of models in a bit more detail. Here I'm just going to list the models and what they mean. So as I said, the full system is a Navier-Stokes equation. So you have a fluid and you have air, and it's coupled by interfacial boundary conditions. And again, this is only tractable numerically and has a very large computational cost. So if you want to do any type of optimization here, you shouldn't. And so what we do is we consider two types of long wave models. One of them is the weighted residuals model, which gives you a PDE for the height and the flux. I'll tell you what these PDEs are in a moment. So these PDEs are tractable numerically, and they're quite accurate representations of the true solution of the problem. Or you can do asymptotic expansions and get a Benny-like equation, which we have seen examples of earlier as well. You can go one step further and do weakly nonlinear analysis. So if you have a very small perturbation from a flat film, you have the Kuromoto-Sivashinsky equation, which I'll tell you a bit more in a second. So before I tell you about the models and what we can do, here's just a comparison. So ideally, we would do everything at the DNS level. So these three plots are for the same, one value of the parameters, which is a bit of an extreme case. On the right, I'm showing you what the DNS looks like of the solution for this. So this is space and time. In the middle, I have a solution to the weighted residuals model. And at the left-hand side, I have the Kuromoto-Sivashinsky equation. And I guess the point of this plot is to say that the DNS takes a while. The other models, I can do them on my laptop in minutes or seconds. But then the moment I go to the simplest model, the chaos equation, the solution doesn't look at all like what it should. So we definitely, I mean, the point that we care about this equation is because we can actually prove things and we can explore a lot there, and there's a lot of literature already on that equation, so it's useful to know what's going on there, but there's no hope on doing controls here and going directly there, but we can do controls here and inform what to do at the next stage, which is hopefully what I'll try to convince you today. And then just a final comparison between the weighted residuals model and the DNS. You can see what the waves look like at the end of the simulation, so when they're saturated, which is the right plot here, so they are qualitatively very similar and there's only very minor errors at the interface. And if I take a point in space and see where the wave is in time, and I plot it here, this is what this plot is, and you can also see that qualitatively the model and the DNS are doing the same thing. So at least at this level, if we develop controls at this level, we have hope that they're going to work in the DNS, and hopefully one day in an experiment. So I'm not going to talk too much about the models. I'll just say what the control is, and I'll start from the bottom. So I'll go back to this hierarchy. I'll tell you what we did here very briefly, and then I'll tell you how we applied that to these types of models and how we're now working at the level of Navier-Stokes equations. So we are considering that we're going to apply controls on the plane. So the fluid is flowing above a plate, and we assume that we have some holes in there, that there's a finite number of them, and from those holes we can pump fluid in or out of the system according to some rule that we can prescribe. So at the level of the Kropotkin equation, this looks like this. It's a very simple model, but the controls appear at the right-hand side. So there's this term bi of x, which is just a delta function. So this tells me I have a control at location xi. And then fi is the control that I can specify. M is my number of controls. So if I have like 5 holes, this m is going to be equal to 5. And this is the equation that I am controlling. So the usual Kropotkin equation just has around a right-hand side 0. So what we can prove here is that there's a lot of, in a longer talk, I talk a lot about the behavior of this equation and what it does. For us, what matters is that there's a lot of possible solutions to this equation. And this is me trying to track some of them. The blue ones are steady states. The red ones are traveling waves. So solitary waves traveling downstream like the one I showed you earlier. And what we can show for this equation is that we can pick any of these. We pick a value of the parameter nu here. We pick any of the solutions, and we can control the system towards that solution as long as the number of unstable modes of the system is, as long as the number of controls is larger than the unstable modes, the number of unstable modes in the system. So we can show that the number of unstable modes depends on this parameter nu here. And so you have, as long as you have as many as them, you can find controls that are like this. So the important thing to remember from this slide is that if I pick a state u bar, I can control it towards there as long as those f functions over there are proportional to the distance between where I am and where I want to be. So I want to be at u bar, I am at u, I have some function k of that distance, it's linear, that drives me towards where I want. So once I have these controls, again, in this case, this is actually something we can prove, and we are sure that this is going to work. There's algorithms we can use to find that function k, and then we can use that to control, for example, the flat solution or any traveling wave solution. So this video here is me stabilizing the previously chaotic solution that I showed you towards a flat solution using a bunch of controls. So the green dots here are the control locations, and if they're green, they're pretty much 0. So in the top, I'll start this again. In the top video, they're all green, so I'm never going to use control here, so I'm just kind of let you see what it would behave like. And in the bottom, I'm controlling it towards flat, which is why there's like very strong colors in here. And then you can see that very quickly the interface becomes, well, very wiggly, and then it will eventually become flat because short waves are stable for this problem. But a more interesting case is when you control traveling waves. So this is the same thing as before, and controlled on top, and then I'm controlling to 3 different traveling waves or solitary wave type solutions using the same type of controls. And here I think I'm using 20 controls because there's 20 stable fields. And again, we explored this as much as we could. We checked for robustness towards having the wrong number of controls, having the wrong parameters. I think I have an extra video here that shows what happens if I predict my parameters wrong. So this is about a 10% error in my parameter, and the solution is still controlled towards the traveling wave that I wanted, which is the red. So I'm trying to make it go red. It's staying in blue, but it's qualitatively doing what I need it to do. But this was, again, this is sort of, I'm going very quickly through this one because what I want to talk about is what we're doing now, which is actually controlling the Navier-Stokes equations via DNS. So once we have that, we've moved on to the long wave models that I mentioned earlier. The long wave models look as follows. So it's the same problem. We have our fluid. We have, say, 5 actuators, so 5 places where we can put fluid in or out of the system. So at the level of the Navier-Stokes equations is a boundary control on the walls. At the long wave level, the controls appear here as the right-hand side, and this is important because this makes the controls very efficient, and that's what makes them robust. And then in the case of the Benny equation, we simply have an equation for Q, which we can differentiate and plug there. And the important thing is that from the surface tension term, we get a fourth derivative. From this term, we get a second derivative. The linearized operator for this equation looks the same as the previous equation. For the weighted residuals model, things are a bit more complicated. Instead of an equation for Q, you get a PDE. So you have to evolve the two equations at the same time. And the controls appear also inside these equations. So these equations are good approximations for the behavior of the full solution. Microphone to the other side. Okay. Better? Thank you. Okay. So they're good approximations for the behavior of the full problem. I guess there's a lot of people in the room that have looked at these types of equations extensively. But the problem with this is that they're so nonlinear. We can't prove anything at this stage. So most of what we've done here was based on linear stability analysis and then testing everything with numerical simulations. So we checked or tried 3 types of controls. So to start with, we just said, okay, the previous controls and the thing that we could prove were proportional to the distance between where I was and where I wanted to be. So now I'm saying where I want to be is capital H, but for most of the rest of the talk, I'm going to be concerned about the flat solution. So think of that capital H as 1. And then what we did were 3 things. The first one was what we now called omniscient and omnipresent, which is assume I can control everywhere and assume I can observe everywhere. So I know what my interface is doing, and I magically can pump fluid in and out of the system everywhere. So this is not very realistic, but it's a case where we can do something. The second case is sort of the same as before. I can observe, I know what my interface is doing everywhere, but I can only apply controls at a finite number of points. And again, this is the same as the previous case, but because the weighted residuals model means solving for H and Q, in theory, I have to observe the flux everywhere as well. No. We know what to do about it, but at the beginning, we were concerned about this. And finally, what you can also do, and this is the most realistic and probably what you could actually do in an experiment, is I can only observe my interface at a number of points with some error, and I can only apply controls at a finite number of points. Okay, this is just to say that, so the first case is easy, or is easier, but all of them are already a bit numerically stiff, so we need to worry about how to solve these problems. Okay, so some examples of what this actually does. So the reason why we cared about this first case, the control everywhere and observe everywhere, is because we can then just assume that the controls are proportional with some constant alpha to H minus 1, and we can work out what alpha needs to be to stabilize a flat solution. So this is just to show that this value of alpha moves eigenvalues of the Benny equation and of the weighted residuals model. to having negative real parts, so everything is unstable. And this is us testing that this works. So this is, if we assume we can control everywhere, we start the Benny model and the weighted residuals model with the same solution, and they are quickly controlled to the flat solution, which is good. I mean, it's not completely unexpected, but we weren't sure it was going to work, and it did, so that's good, which then justified us moving towards the more realistic types of controls. So in this case, we can do some linear stability analysis, but it's not as easy. But the first thing we can do is estimate how many unstable modes there are. So there's a formula that's similar to the previous one, but now it's a bit more complicated. The other one was 1 over square root of nu or something like that. This one now has all the parameters of the problem, such as the domain length, capillary numbers, Reynolds numbers, etc. And we tested what we can do using the exact same methodology as earlier, and everything worked. But what I want to discuss is what we do when we look at case 3, which is finite number of observations, finite number of actuators. So what we're doing here is saying, okay, our control is just like before, some constant alpha times our observation of the interface minus 1, but now the observation at the interface is just at one point. We're not doing things everywhere. And then we also assume that the point where we're observing can be upstream or downstream. So if you have a wave, going down, and you're doing something here, you might actually say, okay, my wave is coming from here, and so I might want to do something based on what the wave is doing there, just because waves travel, and by the time the effect of what you're doing is felt at the interface, the wave may have moved a bit. This is not too important for these types of problems, but it can make a difference if you're controlling with different mechanisms where there's some delay from the control actuation and the interface actually feeling it. So using this type of control and assuming that we have the same number of observations and actuators, we can actually predict then whether the solution is going to be linearly stable or not. So these two plots are the same things for the two models. And what we're doing is applying 3, 5, 7, or 9 controls with strength alpha. And on the y-axis, I have the displacement. And so if you're inside of the curves, we're assuming that the problem is stable, and outside unstable. And so just to see if this works, I just have an example of this working for the models, and then I'll show you what happens at the Navier-Stokes equations, because that's more interesting. So this video here is the interface evolving. What I'm plotting under the interface is the vertical velocity of the fluid in the bulk. And I'm going to let it evolve until t equals 1. I'll move it in a second. And then at t equals 1, I'll start applying controls at 5 points, and you'll see the colors appearing there. And they're just based on that formula earlier with the alpha derived for the Benny equation for the full model. So I managed to do this earlier, but I don't think I'm going to manage to do this now. No, sorry. I'm just going to let it run. It's going to be a bit slow, but anyway. But the point is that by the end of this simulation, this will all become flat very quickly, which is good. I think in the interest of time, I'll show you the nicer results, and at the end, I'll put the video playing, because I only have 4 minutes. So what we're trying to do here, and I guess the whole point of what we wanted to do was go and, well, actually what we wanted was for somebody to do this experiment, but before that we did some DNS. So basically what we tried to do from this was, okay, we have some controls that work very well in this model. What happens if we do the same directly to the DNS? And the first thing we tried, and I don't put the plots here because they're boring, but the first thing we tried was, even at the stage where we could observe everywhere and actuate everywhere, we would just put alpha h minus 1, put it directly in the DNS from the model, So take the controls that we were using at the model and put in the DNS. They started working, you would see the interface going flatter, but then model error would make things go away and go back to whatever it started. So what we did instead was, okay, let's take, again, these types of controls. It's still a finite number of observations and a finite number of actuators, but now my observation is from the DNS, not from the model. So if I just do that, I go through the same process as before. So this plot is the same as before. Let's just look at this one. So this is for 5 controls and one particular value of Reynolds number and capillary numbers. We predicted whether or not the solution would be linearly stable. So we predicted it's going to be stable inside this curve and then stable outside. And then what we did was, okay, put controls of this form with fixed alpha and varying the distance between the actuator and the observer, or fix the distance between the actuator and the observer and make alpha bigger. And so orange circles here means that we managed to stabilize the flat solution, and black circles means that we didn't. So the predictions are actually very good in terms of whether this is going to work or not. And the right plot here is the same as before, so it's h minus flat for the cases that it fails and the cases that it doesn't. So you can't really see the cases that it doesn't because they're all on top of each other. But the way to convince you that this works is to actually show you a video. I'll show you the video first and then explain this plot. So this video is similar to the one before. So on top, I'm going to show you the solution of the weighted residuals model, and in the bottom, the solution of the DNS with the controls derived as before. And they're going to be located at 5 locations. Yeah, model DNS, and then you can see that the solution will go flat quite quickly. So this is a shorter model video because then it becomes boring. But what you see is that the model, because all the controls were predicted for the model decays very nicely. The DNS still decays, but there's all these jumps because there's a model error, so that that's what's creating these jumps. But still, after a very short time, everything works. And then I think just to give you some intuition why the controls won't work directly from the model to the DNS, I'm just showing you the horizontal velocity and the vertical velocity for the model, the DNS, and the difference on the first time step after applying the controls. And what you see is that the horizontal velocity is pretty much the same in both cases, but the vertical velocity has big differences. So because the way to obtain these models is by integrating over the y direction, you are losing some of the physics that's happening, and so you have some errors, and these errors build up, and that's why applying the controls directly doesn't work. So quickly before I finish, I'll just say what we're doing now. So now we're trying to do something a bit better than this. So we have the controls that we used before were like each actuator was communicating with one observer. But there's no reason why we shouldn't do better than that. So we can either have full observations, or we can combine the information that we have from those 5, 7, or whatever points at the interface. So you do that by solving so-called linear quadratic regulator problem. You're still searching for a control that's of the form as before, some function times h minus 1, so h minus the flat solution. And there's a lot of theory and algebra that goes behind this, but these are some plots from our student Oscar, who has applied this to having, I think it was 5 observations and 5 actuators, and just to show that this works and with the right decay. And this plot is similar to what I was trying to say before. What we were trying to do here was, for a range of Reynolds numbers and capillary numbers, try to predict how many controls we need. So that's what the numbers, that's what the red lines are. So below this red line, everything is stable, so we don't care. Between this red line and this red line, we predict that we need 3 controls to work, and then 5, 7, 9, etc. And what we can see is that pretty much everywhere, the number here is smaller than the number that we predict, so we can use less controls. That's what we needed. There's much more things that Oscar did. The paper is just out. Go have a look. It's really nice. So I'll just finish with some conclusions. So we are concerned about feedback control methodology. So we're assuming that we can observe the interface, which may or may not be realistic. But then we're using theoretical results that we can actually prove for very simple models that are not a good model for what we're trying to model. But then we can move these controls above throughout this hierarchy of models to get controls that work and are very robust. And actually, I should have pointed out here that these values of the Reynolds numbers are way beyond what we expect these models to be valid for. We're also looking at using optimal control mechanisms. So that's a paper with Alex that I wish I had presented instead, but next time, where we're using instead of blowing in section controls like I presented, we're using electric fields. So that makes the problem more nonlinear and a bit harder to solve, but we can do nice things here. We're starting to look into limiting the observations a bit more and adding noise to the observations because that's more realistic. And we're trying to find other problems that we can apply this to. So with that, I thank you. I'll put the nice video again. And then you get to see it until the end. And I'll welcome any questions.
Thank you, Susana. Any questions? I got a microphone. Who has questions? Oh, sorry.
No problem. Oh my God.
Hi, thank you. So you made the point when you were looking at the full model control that the reason why you thought it went wrong was because you were losing information when you were averaging vertically. But if I understood correctly, the control you were applying is a vertical blowing and sucking. So do you think it's also related to the nature of the control? I.e., if you chose a different control, could perhaps you do better between the two models?
In the comparisons, you mean? Or in the action? Or
Just actually being able to do better, because you've chosen the direction of the control you've chosen is the one in which you're losing information in the averaging between the.
Yeah, but I mean, we did. Well, the paper with Alex that I was mentioning, we were using electric fields which do not act. They act on the other side, like the perfect dielectric at the other side, and that still happens. Like you start applying the controls, they start working, and then they stop working again.
Okay.
So it's not just that.
It's not just that. There's something more fundamental in there. Okay. Thank you.
If the controls stop working, is there a possibility that the flow will destabilize again?
Yes.
So there is an on and off effect.
Yeah. So they
Thank you.
when by here, for example, there's nothing happening. Or basically what's happening is smaller than whatever resolution that I have in here. Eventually numerical error is going to kick in and it will be. So they're never zero, but they're like 10 to the minus 5 or something like that. So in theory, like I think in an experiment, you could just switch them off and then on again once it starts getting a bit too bad. And you can work out what being a bit too bad means.
Sorry, I think this question I've probably asked every time I give this talk. So when you say you take like the controls from wedge residual and you put them in DNS, that's the actual like injection amplitudes, not the control law that you're doing. So it's not feedback control by the time it's in the DNS. It's like it's pre-computed. Open loop, not closed loop.
No, it's feedback because you're using the observations of the DNS.
Oh, okay.
So I'm taking this formula, which was the formula for before, and then I replaced this by observations of the DNS. I should call this HDNS.
But then, so it's just the alpha that you're using from the wedge residual?
In this case, I'm using the alpha that I worked, that he worked out for. But on the case in the last slide, we are using the matrix K that we used for feedback for the weighted residuals with observations.
Okay, so it is feedback.
Yeah.
Sure. Okay.
Brilliant. Let's just thank Susana again.